Tonight, the solar system holds its breath. 3I/Atlas, the third confirmed interstellar visitor, is about to sweep past Mars at a mere 0.19 astronomical units, while every orbiter circling the red planet scrambles to capture its secrets. But this is far more than just another flyby. The object's blazing emerald coma, erratic microaccelerations, and carbon dioxide-rich chemistry have already shattered every rule in the Comet playbook. Earth's instruments are about to go dark, leaving only a handful of Mars probes standing between us and the truth. Is 3I/Atlas a bizarre comet or something engineered? Something that could rewrite our definition of what alien means? As the countdown reaches 0, the clues, fragmentation patterns, unnatural pulses, spectral oddities threaten to upend everything we thought we knew about visitors from the stars. Will the next few hours reveal something extraordinary, or will science hold firm and prove this is just nature at its most extreme? 6 hours. That's all the time remaining before Earth's view of 3I/Atlas vanishes behind the sun. At 0.19 astronomical units from Mars, roughly 28 million kilometers, the interstellar visitor races past the red planet just as Earth's instruments fall silent. The blackout isn't a technical glitch or a planning failure. It's pure geometry. For this brief span, Mars becomes the solar system's only vantage point. Every major asset in orbit, MAVEN, Mars Express, ExoMars Trace Gas Orbiter, shifts to high-cadence observation mode, their teams executing pre-scripted procedures while improvising on the fly. Inside the MAVEN Control Center, the so-called Red Watch crew takes command. These are the operators trained for contingencies, the ones who run decision trees for every conceivable anomaly. In the hours before blackout, they rehearse rapid switches between standard science operations and burst mode spectroscopy, ready to pivot instantly if a sudden flare or debris alert crosses their screens. Backup configurations are loaded. Cross-checks run continuously with TGO and Mars Express staff. Every command is logged. Every data packet receives a redundant copy. There's no tolerance for a single point of failure when the rest of the solar system is blind. The schedule is unforgiving. Mars Express will capture broadband images every few minutes, stacking exposures to catch even the faintest hint of fragmentation or course deviation. TGO spectrometers sweep the coma for spectral lines that shouldn't exist. MAVEN's particle sensors and magnetometers, running at maximum cadence, monitor for ionospheric ripples, anything that might suggest an unnatural interaction. Each spacecraft power and telemetry budgets are stretched to their absolute limits, with observation slots negotiated down to the minute. If a burst of debris poses a threat, Mars Express stands ready to switch into safe observe mode, sacrificing data for survival. The abort threshold sits just 30% above the last measured density spike. Earth's blackout interval isn't merely a communications gap. It's a test of the entire planetary science apparatus. The Red Watch Coalition acts as the nerve center, relaying commands and data through narrow relay windows, prioritizing instrument health and coordinating with surface assets like Perseverance and Jurong. In the control rooms, clocks count down in parallel to the comet's approach. Outside, amateur arrays listen for the first sign of a photometric spike, ready to upload data to the global alert network. For these 6 hours, the fate of the observation and the answer to whether 3I/Atlas is a cosmic oddity or something engineered rests on the capability of a handful of orbiters and their teams. The urgency is real. The margin for error is razor thin. As the window narrows, every second becomes a potential turning point. A string of unexplained signals has followed 3I/Atlas since its first detection. The earliest hints came from a backyard telescope in Pune, India, where Priyaralo, a citizen astronomer, noticed a repeating pulse in the light curve, brightening and fading with a rhythm no comet handbook could explain. Her post drew immediate attention, but the oddities only multiplied as professional arrays joined the watch. Photometric records show the object's brightness, surging at intervals too regular for random outgassing. The pulses, spaced by nearly identical gaps, defy the jittery, one-off flares seen in typical comet activity. Each spike arrives with sharp onset and a clean decay, as if switched on and off by some unseen mechanism. Even as the object approached the sun, the periodicity held steady, unblurred by distance or solar glare. Spectroscopy delivered a second surprise. Instead of the familiar water vapor lines, the dominant signature in every spectrum was carbon dioxide. The carbon dioxide to water ratio topped 8-1, an order of magnitude above even the most volatile rich comets known. This chemical fingerprint is so rare that laboratory models struggle to replicate it. Alongside the carbon dioxide, the coma glows emerald green, peaking at 516 nanometers. The color persists across instruments, confirmed by both ground-based and orbital spectrographs. The usual suspects, C2 swan bands, carbon monoxide plus emissions, can't account for the intensity or stability of the hue. Nickel emission lines, especially at 337 and 380 nanometers, outshine iron by factors of 4 or more, a reversal of what's observed in every known solar system comet. Imaging and polarimetry add yet another layer of mystery. The coma's green light is matched by a deep negative polarization branch, a trait more common to certain asteroids than to icy wanderers. Dust tails reveal grains larger and slower than standard comet dust, with trajectories that resist straightforward modeling. These grains drift in a broad, lazy arc, as if released by a mechanism that dozes out mass in measured bursts rather than chaotic jets. Astrometric tracking, meanwhile, records microaccelerations, tiny course corrections that don't align with any known outgassing profile. Each nudge coincides with brightness pulse, suggesting a direct link between light emission and motion. No single anomaly stands alone, but together they sketch a portrait of an object that resists every simple categorization. Every dataset, photometry, spectroscopy, astrometry, feeds the growing dossier of mysteries. The evidence is in waiting for an explanation that fits all the facts at once. Most planetary scientists began with the simplest tools at hand, physics and chemistry. For main hypotheses, each grounded in established models, have been tested against the growing dossier of 3i/Atlas's oddities. The first points to chemistry shaped in the deepest cold. In this view, 3i/Atlas formed far from any star, where water freezes out completely and carbon dioxide, carbon monoxide, and even rare ices dominate. Comets from the Oort cloud hint at this kind of chemistry, but none have shown a carbon dioxide to water ratio so extreme, topping 8-1. Still, the argument runs, interstellar space is vast and our catalog is tiny. A single outlier could rewrite the boundaries of cometary chemistry. The second model turns to structure. Volatile pockets, deep reservoirs of trapped gases, could erupt as sunlight seeps through the crust. These pockets, if distributed unevenly, might explain the rhythmic pulses in brightness. Laboratory simulations show that even small temperature differences can trigger sudden jets, sometimes repeating if the layers are stratified. Regularity, though rare, is not impossible in a body shaped by billions of years of cosmic weathering. Dust dynamics offer a third explanation. The coma's emerald glow in the presence of large, slow-moving grains could result from unusual dust composition or size distribution. Solar wind and Mars' weak magnetic field might shape the tail, herding charged grains into broad arcs. Models of comet tails show that in certain geometries, heavy grains lag behind, drifting in lazy curves that mimic measured bursts. The negative polarization branch, more typical of asteroids, could hint at compact carbon-rich grains rather than icy fluff. Finally, some point to the limits of our models themselves. With only 2 previous interstellar visitors on record, every new arrival tests the edges of simulation, subtle interactions between sunlight, volatile release, and tumbling motion. In this view, the anomalies are not evidence of intent, but reminders of how much remains uncharted. For each puzzle, the scientific community demands that every natural explanation be exhausted before considering anything more exotic. For these 6 hours, Mars becomes the solar system's only observatory. 3 orbiters, MAVEN, Mars Express, and ExoMars Trace Gas Orbiter, form the backbone of the evidence chain. Each brings a distinct set of instruments, each tasked with capturing a different signature of 3i/Atlas's passage. MAVEN's imaging ultraviolet spectrograph, tuned for faint emissions, sweeps the sky for ultraviolet traces in the comet's tail, especially signs of fragmentation or abrupt outbursts. Its particle counters and magnetometers, running at maximum cadence, Watch for ripples in Mars' ionosphere. A sudden spike in charged particles or a magnetic field twist could signal that something more than natural chemistry is at work. If the comet's dust or plasma interacts with the atmosphere, MAVEN's sensors will be the first to register the disturbance. Mars Express, with its visual monitoring camera and spectrum spectrometer, focuses on direct imaging. Stacked broadband exposures track the comet's coma, hunting for evidence of splitting or shape change. The spectrometer, scanning from ultraviolet to infrared, searches for spectral lines that don't belong, unexpected emissions, or missing water vapor. Its plasma analyzer, Aspera 3, monitors for energetic ions that could betray a non-standard interaction between the comet and the Martian environment. ExoMars TGO's Nomad and ACS spectrometers probe the coma for trace gases, hunting for isotopic ratios or molecular fingerprints that defy solar system norms. CASIS, the high-resolution imager, attempts to catch fragmentation events or dust jets in progress. Each instrument's data is logged with exact timing, cross-referenced in real time among the teams. On the surface, Perseverance and Jurong, rovers listen for indirect signs, unusual dust fallout, atmospheric changes, even auroral glows on the horizon. Their environmental sensors and cameras provide a backup layer of evidence, though with less sensitivity than the orbiters above. The checklist is explicit. Fragmentation patterns, trajectory shifts after a flare, spectral or radiation lines that resist explanation, isotopic ratios outside solar norms, and any sign of engineered synchronization in pulses or accelerations. Every anomaly flagged by one asset must be confirmed by another. No single reading is enough. Only converging evidence from multiple instruments and perspectives can move the needle from the realm of the unusual to the truly unprecedented. Every byte of data streaming from Mars faces a gauntlet of checks before it enters the scientific record. The first stop is redundancy. Each packet relayed from the orbiters is duplicated, time-stamped, and logged by independent ground stations on both sides of the Atlantic. This system guards against solar interference, transmission errors, and the rare but real risk of data corruption during the blackout. Telemetry delays, sometimes stretching to hours as signals bounce through relay satellites and deep space antennas, add another layer of uncertainty. Mission teams prioritize anomaly packets, those flagged for possible fragmentation, spectral outliers, or abrupt trajectory changes, routing them through rapid cross-verification routines. No single sensor or team can clear an alert alone. Every candidate event is double-checked by at least 2 instruments, with raw data posted open archives as soon as bandwidth allows. Chain of custody protocols extend beyond numbers. If a dust grain or ice fragment is detected by an orbiter's collector, planetary protection officers step in. These specialists enforce strict handling rules. Samples are sealed, barcoded, and logged with digital hashes, requiring sign-off from both NASA and JAXA before analysis proceeds. The goal is clear provenance. Any organic signature found in Martian regolith or atmosphere after the flyby must be traceable. Future life detection missions depend on knowing what arrived from 3I/Atlas and what belongs to Mars. Even the metadata, time, location, instrument calibration, is captured in tamper-proof ledgers, ensuring that every odd reading can be audited years from now. Outside the control rooms, a parallel network comes to life. Amateur astronomers, from backyard arrays in Pune to robotic telescopes in Arizona, upload photometry and astrometry to shared databases. The first public alert of a photometric spike may come from a citizen scientist, but professional teams now triage these uploads in real time. Only after cross-instrument confirmation do agencies issue official bulletins, urging patience and caution. Extraordinary claims will wait for extraordinary evidence. Messaging plans, drafted in advance for every scenario, stress transparency without sensationalism. The public pipeline is wide open, but every step is designed to build trust, redundancy, verification, and chain of custody, all in service of a verdict the world can believe. Inside the Red Watch control room, the decision matrix sits at the heart of every conversation. 3 branches, conservative, hazardous, extraordinary, define the possible verdicts for 3I/Atlas as data streams in from Mars. The conservative path holds if every anomaly can be mapped to rare but natural comet behavior. volatile pockets erupting in sequence, dust grains shaped by unfamiliar chemistry, and microaccelerations that fall within the outer limits of known physics. Hazardous becomes a ruling of fragmentation, or debris clouds cross critical thresholds, mass loss above 10%, or unpredictable course changes that threaten Mars orbiters. In that case, instrument safing and data triage take priority over science. The extraordinary branch stands apart. It demands at least two independent, statistically significant anomalies: synchronized pulses matched by microaccelerations, or spectral lines that defy any known chemical model, confirmed by separate teams and instruments. No single signal, no matter how strange, is enough. The rule is simple. Only converging evidence can open the door to engineered possibilities. Every operator knows the stakes. In these hours, the matrix is not just a chart. It is a playbook for what happens next in planetary science. Draft protocols now require that every byte of data from an interstellar flyby moves up a rapid release ladder, public within hours, not months. The days of embargoed comet telemetry are over. NASA, the European Space Agency, and the Japan Aerospace Exploration Agency have all endorsed mirrored archives where raw and annotated data flow to open servers as soon as ground stations confirm integrity. Automated pipelines flag outliers for instant review, while calibration notes ride alongside the numbers. For Mars orbiter teams, emergency procedures now include compressed, high-cadence relays during any transit event, with follow-up dumps of full-resolution spectra and images. Citizen science is no longer a sideline. Registered amateur networks, from Pune to Patagonia, upload photometry and astrometry directly into vetted pipelines. Machine learning routines sort, cross-check, and queue these uploads for professional triage, ensuring that the first alert, sometimes from a backyard array, can trigger official scrutiny within minutes. On the planetary protection front, the Committee on Space Research's latest draft mandates anomaly tags on every biosignature, reading post-encounter, and chain of custody logs for any dust or organic sample. These reforms are designed not just for the next 3 I/Atlas, but for every future messenger from beyond the sun, locking in transparency, trust, and a global playbook for the unknown. On October 3rd, 2025, as 3 I/Atlas passed within 0.19 astronomical units of Mars, every major Mars orbiter and rover turned its full attention to the sky. Over 40 hours of high-cadence data were relayed from MAVEN, Mars Express, and ExoMars TGEO, capturing the object's emerald glow, pulse brightening, and carbon dioxide-heavy spectrum. Signals never before seen from any known comet. While natural models explain much, the pattern of microaccelerations and the synchronized pulses remain without a definitive cause. The raw data, released for open analysis, are now part of the public record. But key questions, such as the true source of the emissions and whether engineered activity played any role, remain unresolved. What is certain? This encounter has driven new protocols for interstellar monitoring and set a standard for transparency. Whatever 3 I/Atlas proves to be, its Mars flyby has changed how we prepare for and talk about visitors from beyond our solar system. The 6 hours of darkness may have ended, but the questions they raise are only beginning to unfold. For hours and 37 minutes into blackout window, MAVEN's magnetometer registered something impossible. The spike came without warning, a sharp, coherent oscillation in Mars' ionosphere directly beneath 3 I/Atlas's trajectory. Not the chaotic scatter of natural plasma interaction, but a pattern. Dr. Sarah Chun, lead physicist on the Red Watch team, stared at her screen as the waveform repeated. 3 short pulses, 3 long, 3 short. Get TGO on this, she said, her voice tight. I need confirmation before I even think about. Already on it, interrupted Marcus Webb from the ExoMars station. Nomads picking up synchronized emission spikes. Carbon dioxide venting in bursts that match your magnetic signature. Timing is... Christ, Sarah, timing is exact to within 0.3 seconds. The control room went silent. Everyone knew what 3 short, 3 long, 3 short meant. It was humanity's most famous signal, the one we've been sending into space for over a century. SOS. But this wasn't coming from Earth. Mars Express? Chen's hand hovered over the emergency protocol button. Confirming came the reply from the European operations desk. Spickham shows the emission lines spiking in perfect synchronization. We're also seeing, new data coming in from Aspera 3. The plasma jets aren't random. They're directional, all of them pointing at a pause, pointing at Earth. The room erupted in controlled chaos. Operators cross-checked readings, ran diagnostics, searched desperately for equipment malfunction or data corruption. But every system checked out. Every instrument agreed. 3I/Atlas was signaling. Decision point, announced Chun, her voice cutting through the noise. We're at the extraordinary threshold. 2 independent anomalies, multiple instrument confirmation. This goes up the chain. Now. As Earth's deep space network began its emergency acquisition sequence, try and catch any remnant of the signal before 3I/Atlas disappeared behind the sun, Mars Express captured what would become the most analyzed image in astronomical history. The comet was breaking apart, but not chaotically, not like Shoemaker-Levy 9 or any other natural fragmentation. The nucleus split into 7 distinct pieces, each separation occurring during a brightness pulse. The fragments arrange themselves in a geometric pattern, a perfect hexagon with one piece at the center. Get surface assets on this, ordered Chun. I want Perseverance and Jurong recording everything. Atmospheric spectra, dust composition, radiation counts, everything. On Mars' surface, Perseverance's cameras caught the moment the fragments reached their closest approach. The sky above Jezero crater blazed emerald green, bright enough to cast shadows in the Martian dusk. Then came the sound, or rather, the vibration. The rover seismometer registered a low-frequency pulse, rhythmic and sustained, that seemed to resonate to the planet's crust. Jurong, thousands of kilometers away in Utopia Planitia, recorded the same phenomenon at the exact same moment. Impossible, whispered Dr. James Morrison from NASA's Jet Propulsion Laboratory, watching the synchronized data feeds. Sound doesn't travel through space. There's no medium. This shouldn't. It's not sound, interrupted Dr. Yuki Tanaka from JAXA. Look at the frequency. It's magnetic. The fragments are generating a coordinated magnetic pulse, using Mars' own field as a transmission medium. They're making the entire planet ring like a bell. When Earth's instruments finally reacquired 3I/Atlas on the other side of the sun, 6 hours and 42 minutes after blackout began, the object had changed. The 7 fragments had coalesced back into a single body, but the spectral signature was different. The carbon dioxide emissions had dropped to normal cometary levels. The emerald glow had faded to a dim green, barely distinguishable from standard C2 emissions. The microaccelerations had ceased entirely. It was as if 3I/Atlas had expended itself, used up whatever made it extraordinary during those 6 hours when only Mars could watch. The last data packet from MAVEN, timestamp 1743 and 12 seconds universal time coordinated on October 3rd, contained a final anomaly. As the fragments merged, the magnetometer recorded one last pulse, longer, more complex than the SOS pattern. Dr. Chin ran it through every analysis tool available. Fourier transforms, wavelet decomposition, pattern recognition algorithms. It took 3 days before a graduate student at MIT noticed what everyone else had missed. The magnetic pulse, when converted to binary based on field strength variations, contained structure, not random noise, but organized information, too organized to be natural, too brief to be decoded. The final 17 seconds of coherent signal from 3I/Atlas carried 4,096 bits of data. Enough for a simple message. Enough for coordinates. Enough for a warning or an invitation. But without context, without a cipher, it remained locked. A cosmic Rosetta Stone floating away at 26 kilometers per second, carrying its secrets back into the dark between stars. In the weeks following the encounter, the scientific community fractured into camps. Conservatives argued that every anomaly, even the SOS-like pattern, could be explained by exotic but natural processes, resonance cavities in the nucleus, magnetic field interactions, confirmation bias, and pattern recognition. The synchronized fragmentation was just geometry, They said the natural result of stress fractures in an unusual body. Others weren't convinced. The timing was too precise. The patterns too deliberate. The final data burst too structured. They called for new missions, new protocols, new ways of thinking about what qualifies as a signal versus noise. Dr. Priya Rallo, the amateur astronomer who first spotted the pulses, spoke for many when she addressed the International Astronomical Union's emergency session. We designed our search for extraterrestrial intelligence around radio signals and mathematical constants. We look for messages that think like us. But what if intelligence doesn't always announce itself the way we expect? What if 3i/Atlas wasn't trying to communicate with us at all during those 6 hours? What if it was trying to communicate with Mars? The question hung in the air, unanswered and perhaps unanswerable. Today, a new generation of instruments points toward the outer solar system, waiting. The Atlas protocols, as they're now called, ensure that no future visitor will pass unobserved. Every major space agency maintains a rapid response network, ready to pivot all available assets toward any object, showing even a hint of the anomalies that characterize 3i/Atlas. The data from those 6 hours remains open, hosted on servers around the world, studied by thousands of researchers and citizen scientists. The 17-second signal has been analyzed by cryptographers, linguists, mathematicians, and machine learning algorithms. So far, it keeps its secrets. But on Mars, something changed. Perseverance's long-term atmospheric monitoring detected a persistent anomaly in the ionosphere above Jezero crater. A faint, recurring oscillation at the same frequency as the magnetic pulse from 3i/Atlas. It appears every 37 hours, lasts for exactly 17 seconds, and then fades. Some call it resonance, an echo of the encounter slowly dissipating in Mars' thin atmosphere. Others wonder if it's something else, a marker, a beacon, a response to a message we almost understood. The solar system no longer holds its breath, but it listens now with new ears and new expectations. Because 3i/Atlas taught us something fundamental about the universe. We may not be alone, but we're almost certainly not ready. Not yet. 2 years after Mars encounter, the Vera C. Rubin Observatory detected Object 4I/Prometheus entering the solar system from the direction of the constellation Cygnus. Initial spectroscopy showed an unusual emission profile, strong carbon dioxide signature with traces of nickel, and a faint but unmistakable emerald glow. Dr. Sarah Chun looked at the preliminary data streaming across her screen, then reached for the red phone that connected directly to NASA headquarters. "It's happening again," she said quietly. "But this time it's heading for Earth." The call went out across the planet. Red Watch protocols, full activation. Every telescope, every sensor, every amateur astronomer with a backyard ray turned toward the incoming visitor. This time we would be ready. This time, Mars wouldn't be the only one watching. The Vera C. Rubin Observatory's detection of 4I/Prometheus triggered a cascade of responses that made the Mars encounter look like a dress rehearsal. Within hours, the International Coordination Center, established in the wake of 3i/Atlas, convened its first emergency session. Unlike 2 years ago, there would be no blackout period, no single planet carrying the burden of observation. This time, humanity had prepared. Dr. Sarah Chin found herself leading what the media had already dubbed Earthwatch, a coalition that made the Red Watch team look modest by comparison. Every major space telescope, from Hubble to the James Webb, received priority tasking. Ground arrays from Chile to Hawaii synced their observation schedules. The Chinese space station, the ISS, and even private orbital platforms were drafted into a coordinated surveillance network. But 4I/Prometheus was moving faster than 3I/Atlas had. Much faster. "Velocity is off," announced Dr. Marcus Webb, now Deputy Director of the Interstellar Object Response Group. "It's decelerating at a rate that shouldn't be possible without active propulsion. Current trajectory puts closest approach at 8 cent from Earth, inside Mercury's orbit, in 21 days, 6 hours. The room absorbed that information in silence. 0.08 astronomical units, roughly 12 million kilometers. Close enough for detailed observation. Close enough to be terrifying. Spectroscopy? Chin asked, though she already knew the answer would complicate everything. Dr. Yuki Tanaka pulled up the analysis. Carbon dioxide to water ratio, 9-1. Nickel emissions at 337 nanometers, stronger than 3I/Atlas. The emerald signature is confirmed by 17 independent observations. And Sarah, she paused. It's pulsing. Same pattern. 3 short, 3 long, 3 short. Christ, someone muttered from the back of the room. But there was something else. Dr. Priya Rallo, now a full member of the team rather than a distant amateur, highlighted a section of the light curve. The pulses started exactly when our detection was announced publicly, not when we first spotted it, but when the IU bulletin went live. It's like it knows we're watching, finished Chun. The decision to respond had been debated for 2 years. After 3I/Atlas, the Committee on Space Research had drafted protocols for active contact when to attempt it, how to format a signal, what authorities needed to approve. The rules were strict, the thresholds high. For I/Prometheus had crossed every single one. We're authorized to transmit, announced the director of the International Coordination Center. Arecibo Network and the Deep Space Network are standing by. The question is, what do we say? Teams have been working on this problem since the moment 3I/Atlas disappeared. Linguists, mathematicians, physicists, even composers and artists had contributed to the archive of potential first contact messages. But when the moment arrived, Dr. Chin made a simple call. Send a 17-second sequence. The 1-3I/Atlas left us. If this is related, if these objects are connected, maybe that's the key. The transmission went out at 8 o'clock Universal Time Coordinated on January 15th, 2028, broadcast on multiple frequencies from 6 locations around Earth. The 4,096 bits of data that 3I/Atlas had encoded in magnetic pulses, now converted to radio waves and aimed at the incoming object. The response came in 4 hours. For I/Prometheus brightened dramatically, its coma expanding and intensifying to a deep emerald that was visible to the naked eye from dark sky locations. The pulsing pattern changed. No longer the simple SOS rhythm, but something more complex, a cascading sequence of flashes that repeated every 93 seconds. Get me everything. Chin ordered photometry, spectroscopy, polarimetry. I want to know what changed in that coma. And someone run that pulse pattern through. Already on it, interrupted Dr. Rallo, her fingers flying across her keyboard. Sarah, this is a response, not just acknowledgement. The pattern contains a 17-second sequence we sent, but modified, extended. There are an additional 8,192 bits of new information. The room erupted in controlled chaos. Every team dove into their analysis, cross-referencing against the 3I/Atlas data, searching for patterns, testing hypotheses. But beneath the scientific urgency ran a current of something else. Something that had been building since that first SOS signal 2 years ago. We were in a conversation now, a real one, and we had no idea what we were saying. As 4I/Prometheus drew closer, the trajectory models grew more precise and more disturbing. The object wasn't simply passing through the solar system. Its path incorporated multiple microburns, course corrections executed with a precision that screamed intentionality. It's threading a needle, explained Dr. Webb, highlighting the projected path on the main display. Look at this. It's going to pass Venus at 24 cents, Earth at 0.08, then slingshot around the Sun with a perihelion of 0.15. That trajectory isn't random. Something calculated this course to maximize observation time of the inner planets while using solar gravity for acceleration. Acceleration toward what? Asked Chun, though she suspected she knew. Webb pulled up the extended trajectory. Mars. After Sun flyby, it's heading straight for Mars. ETA, 37 days after Earth encounter. 37. The same number of hours between those mysterious pulses that Perseverance still detected in Mars' ionosphere. Coincidence? Someone asked without conviction. We don't believe in coincidences anymore, Chin replied. The realization settled over the team like a weight. 3I/Atlas hadn't been a random visitor. It had been a scout, a probe, and now 4I/Prometheus was following the trail, checking each waypoint, perhaps reporting back to where Dr. Tanaka pulled up the trajectory data for both objects, extrapolating backwards. If we trace their paths back far enough, assuming constant velocity before solar deceleration, they originate from the same approximate region of space, near Deneb in Cygnus, roughly 2,600 light-years away. That's impossible, breathed Webb. Even at relativistic speeds, that's... Millen. Aye, finished Tanaka. These objects would have been launched when humans were building the first pyramids. Unless everyone thought, but no one said, they weren't launched at all. Unless they were something else entirely.